Hi, my name is Talia Nasi. I'm a Senior Developer Advocate here at AWS Serverless. Today we'll be talking about building event-driven applications with Amazon EventBridge. In modern application development, event-driven architecture is becoming more prominent because it can make building applications in the cloud easier. Event-driven architecture can allow you to decouple your services, which increases developer velocity and can make it easier for you to debug your applications. It can also help remove the bottleneck that occurs when features expand across different teams, which allows teams to progress more independently. One way to think about how an application works is as a system that reacts to events from other places, like from within your application or from outside of your application. In this approach, you focus on the system's interaction with its surroundings as a transmission of events. The application receives and creates events, inputs to the application, and outputs from the application act as events. In event-driven applications, you have the event producer, the event bus, and the event consumer. The event producer is the event source where the events come from. This can be an AWS service, a custom event, or an event that comes from a third-party SaaS app. The event bus acts as an event router to route the events to where they need to go, and the event consumer or event target listens for events and acts only upon the events they are interested in. A common way of making components of an application work together is through an API-driven request-response architecture where you have requests and responses. For example, you query a list of orders from an Orders API, and the Orders API responds with a list of orders. This is an example of synchronous architecture. The system asking for the orders waits for the response. You cannot move on until the response comes back. In this approach, you send commands that are directed to a target. For example, place this order or add this record to the database. API thinking is synchronous thinking. You cannot move on until the API response comes back. With APIs, you send commands. Do this thing. It has an intent and it's directed to a specific target. An example of this would be create this account or add this product to the shopping cart. An event, however, is something that happened. Maybe a new file has been created, maybe an exception or error occurred, maybe a new customer has been created, maybe a new order has been inputted into the system. It tells you a fact. Events are also immutable, which means they cannot be changed. So for events, you describe a fact, and it's something that happened in the past, and then others can decide what to do with it. In a synchronous model, shown on the left, the client makes a request to Service A calls Service B, and then Service A needs to wait for Service B to respond before it continues on and eventually responds to the client. In synchronous event-driven architecture, there is no response path. The service surfaces the event and then immediately moves forward. The trade-off here is that there's no direct channel for Service B to pass back information to Service A besides confirming it received the event. But in many cases, you do not need that explicit coupling between the request and response channels. An event is something that happened. For example, a new record is added to a DynamoDB table, or an item is put into an Amazon S3 bucket, or an API is hit. Events are also immutable, which means you cannot change them. Once an event happens, you cannot undo it. For example, if there is an event raised when an order is placed, there can be another event for an order being canceled. You cannot undo the first event. Events can come from various places, such as messaging systems or databases, both within and outside of your application. Events are JSON objects that tell you information about something that happened in your application. In event-driven architecture, events represent facts. Each component of the application raises an event whenever anything changes. Other components listen and decide what to do with it and how they would like to react to this state change. Events are observable. Any service that is authorized can watch an event. Consider a coffee shop example where there is a barista who makes coffee and a pastry chef who makes pastries. When a customer enters the coffee shop and orders a cup of coffee, the barista starts to make the coffee and the pastry chef takes no action. However, if a customer comes into the coffee shop and orders a chocolate croissant, then the pastry chef starts making the chocolate croissant and the barista takes no action. The pastry chef is only interested in orders relating to pastries, and the barista is only interested in events relating to coffee. Here's an example of what an event could look like. In the events shown, S3 raises the event when you put an item into this S3 bucket. The event source is this S3 bucket named SAM App Source Bucket, and the object that is put into the bucket is called brad.jpg. Many applications are built in a monolith, where the components are tightly coupled and are highly dependent on each other. This proves to be problematic when there are bugs and you're trying to pinpoint exactly what part of the application is failing. Decoupled architectures are composed of components or services that are loosely coupled. In an event-driven decoupled architecture, you broadcast events without caring who responds to them. This saves time because events can be queued and forwarded whenever the receiver is ready to process them. This allows for building scalable, highly modifiable systems. Decoupled applications enable teams to act more independently, which increases their velocity. For example, with an API-based integration, if my team wants to know about some change that happens in another team's microservice, I have to ask that team to make an API call to my service. That means I have to deal with authentication, coordination with the other team over the structure of the API call, etc. This causes back and forth between the teams, which slows down development time. With an event-driven application, you can subscribe to events sent from a microservice, and the event router takes care of routing the event and handling authentication. Decoupled applications also allow you to build new features faster. Adding new features or extending existing ones is simpler with event-driven architectures. This is because you might only have to choose the event you need to trigger your new feature and subscribe to it. You may also just need to modify your existing event to add new functionality. When you build applications using event-driven architecture, often you write less code because you only need to consider new events, as well as which service is subscribed to those events. For example, if you are building new features for your application, all you have to do is consider the existing events and then add senders and receivers as necessary. You may need to add a new event, but you can also see which events already exist. In this way, you speed up development time because each functional unit is smaller and there is often less code. You also get better extensibility with event-driven architecture. Other teams can extend features and add functionality without impacting other microservices. Producers of events have no knowledge of event consumers, which can help simplify the microservice logic. A common process to build applications is to work with your product managers and business stakeholders to gather requirements. Developers then translate those requirements into code. However, there may be a disconnect between the product requirements and the code. When you use events, everyone in the business understands the logic. You define the events in an application. For example, a customer adds an item to their shopping cart, or a customer account is created. And that becomes your product requirements. Whenever that action happens, it produces an event, and whoever is interested can take action on that event. For example, a marketing manager could be interested whenever a customer creates a new account. One way to choreograph this in event-driven architecture is to have a marketing event bus that listens for the new account event. There could also be other teams that are interested, such as the analytics team, who also subscribe to that event. Each team or service can subscribe to events that are relevant to them. Event-driven architecture is a great way for businesses to describe their business problems and represent them. In event-driven architecture, services interact with each other through events. Again, an event is something that happened in your application. They are JSON objects that tell you information about that state change that happened in your application. When you build applications with event-driven architecture, you decouple your event sources and event targets. Decoupling event sources and event targets can greatly speed up development time, and it can simplify making changes to your applications. For example, let's say you are a developer at an e-commerce company and you're building a serverless e-commerce application. Your team is in charge of the account creation and authentication process. You build the login flow and raise an event when a new user creates an account. When the event is raised, other teams can be alerted. The marketing team can listen for the account created event and take action on it. For example, they can send promotional emails or discounts. In this decoupled architecture, event producers and consumers don't have to know about each other. They only have to listen to events and act accordingly when they are interested in an event. This can speed up development by reducing the complexity caused by building new features. In event-driven applications, you have the event producer, the event bus, and the event consumer. The event producer is the event source that the events come from. The event bus acts as an event router to route the events, and the event consumer listens for events and acts only upon the events they're interested in. In AWS, events are choreographed through Amazon EventBridge rules. A rule matches incoming events from an event source and sends them to event targets for processing. Amazon EventBridge accepts events from many different event sources, including over 200 AWS services, custom events from your Lambda functions or applications, and third-party SaaS applications. You specify an action to take when EventBridge receives an event that matches the event pattern in the rule. When an event is raised that matches the rule, EventBridge sends the event to the specified target and triggers the action defined in the rule. To route events from these sources to the correct target, the events must be placed on a corresponding event bus. There are 3 types of event buses. The first type is the default bus, which is always available in every account, and it's where AWS events are routed to. The second is a custom event bus. You can create a custom event bus for your own applications to meet your own business needs. Lastly, you can also create SaaS event buses, which are created when you configure SaaS applications as an event source. There are many potential event targets. Event targets are what the event bus route to once a corresponding event happens. Targets include Lambda, Amazon Kinesis, AWS Step Functions, Amazon API Gateway, and even event buses in other accounts. This flexible design allows you to create a wide variety of integration patterns based on your specific needs. In this tutorial, we will send an event from Amazon S3, the event source, to AWS Lambda, the event target, using an event rule. In this tutorial, you learn how to configure events with Amazon EventBridge by deploying an AWS SAM template. The AWS Serverless Application Model, or SAM, is an open-source framework for building serverless applications. It provides shorthand syntax to express functions, APIs, databases, and event source mappings. SAM is an extension of CloudFormation, which is the AWS Infrastructure as Code tool. You define resources using CloudFormation in your SAM template and use the full suite of resources, intrinsic functions, and other template features that are available in CloudFormation. When you deploy your SAM template, it gets transformed, all of the resources get transformed into CloudFormation resources. First, you will upload images to an S3 bucket. This raises an event which invokes a Lambda function, which then resizes the image and places it in a different S3 bucket. The only prerequisite for this tutorial is to have the SAM CLI installed on your machine. If you use AWS Cloud9, this is already installed for you. First, navigate to the Serverless Land Patterns collection at serverlessland.com/patterns. Filter by SAM, and then choose the services EventBridge and S3. Then choose the pattern S3 to EventBridge to Lambda. This SAM template deploys an S3 bucket, a Lambda function, an EventBridge rule, and the IAM resources required to run the application. Click on the cloning instructions to copy it. Then paste the cloning instructions in your terminal and run sam deploy -- guided to deploy the pattern. The change set that's created shows you the difference between what's in production now and what you're deploying. You can look at the different resource statuses below, and you'll see a list of the resources being deployed. This process can take a few minutes, but once the stack has finished deploying, you'll see this success message. Next, navigate to the EventBridge console and choose Rules from the left panel. Then, choose the rule that was created by AWS SAM that starts with sam-app. The event source is S3, and the rule is invoked when an image is put into the source bucket in S3. Next, notice that the event target is the Lambda function that you created from the SAM template. Navigate to the S3 console and choose Buckets on the left panel. Then choose the bucket that was created for you from SAM, choose the Properties tab, and note that the integration with Amazon EventBridge is on. From the Objects tab, choose Upload and upload an image. Next, navigate to the Lambda console and choose your Lambda function. Select the Monitor tab and choose View Logs in CloudWatch. You can see the event that triggered the Lambda function in the logs. In the previous example, you add an EventBridge rule that routes events from S3, the event source, to Lambda, the event target, using an event bus. Now, let's add another rule. From the EventBridge console, choose Rules and then choose Create Rule. Enter a name and description for the rule. Then define the event pattern that is used to invoke the event targets. For service provider, choose AWS, and for service name, choose S3. For event type, choose Amazon S3 Event Notification, and in the Event dropdown, choose Object Created. You are configuring the event source to be an object created in your S3 bucket. Select either the default AWS event bus or a custom event bus. Select the event target. In this example, configure Amazon CloudWatch log group. Enter any name for the log group, which is created automatically for you. Then choose Create Rule. Next, upload an image to the S3 bucket. Navigate to the Amazon CloudWatch console after you upload an image. From the CloudWatch console, choose Log Groups from the left panel. Then choose the log group that you created and choose this log stream. Here you can see the event is logged to CloudWatch logs. What's important to notice here is that adding a second event rule did not change the event source's behavior or affect other event targets. Next, we will perform an event discovery exercise. We'll go through how to create a schema registry with EventBridge and how to represent an event as an object in your code to use in your application. The first step in identifying these events is to work through the process of event discovery. In this process, you decide the events that the event source produces and what parts of the application must know about those events. Event schemas describe the structure of an event and fields included in the event. If the event's contents match the event target's requirements, the event service sends the events to the target. If you have an existing application that you want to discover event schemas automatically for you, you can enable the Amazon EventBridge Schema Discovery. If you are building a new application, you can conduct an event discovery exercise. An event bus connects the event to the subscriber. The event bus at AWS is Amazon EventBridge. Use EventBridge to choreograph interactions between event sources and event targets. Notice that events are not technical or focused on implementation. Rather, they are real-world things that happened in your system. This is because everyone, from developers to product owners, must understand them. In the event discovery phase, events act as your business requirements. Later, developers then translate those requirements into code. Once you have the events laid out, you decide who is interested in each event. For example, consider the events listed for an example e-commerce application: account created, item added to cart, and order placed. Whenever a user creates an account, the marketing team subscribes to that event to send the account holder promotions and discounts. The security team encrypts the account holder's username and password into a database to save the account credentials. Whenever a user places an order, the system sends a message to the fulfillment team to start packing and shipping the order. This approach decouples the interactions between all of these services. This decoupling is beneficial because it increases developer independence by reducing the dependencies on other teams to write integrations. Once the initial event schema planning is complete, you want to ensure that developers can continue to build new features without needing to coordinate with other teams closely on event schemas. For this reason, EventBridge's schema registry and automated schema discovery can help developers quickly build new features based on their application's events. You use EventBridge schema registries to search for, find, and track different schemas generated by your application. You can also automatically find schemas with the automated schema registry. Applications can have many different types of events. Events generated from AWS services, third-party SaaS applications, and your custom applications. With so many event sources, it can be challenging to know what to expect when consuming events. A schema represents the structure of an event. It describes what happened in the event, where the event came from, and the timestamp. The event schema is important for developers as it shows what data is contained in the event and allows them to write code based on that data. For example, an order placed event might always contain a list of items in the order as an array and a user ID as an integer. EventBridge helps automate the manual process of finding and documenting schemas. There are two capabilities to highlight: schema registry and schema discovery. A schema registry is a repository that stores a collection of schemas. You can use a schema registry to search for, find, and track different schemas used and generated by your application. AWS automatically stores schemas for all AWS sources for EventBridge in your schema registry. SaaS and custom schemas can be generated and added to the registry using the schema discovery feature. A schema registry enables you to use events as objects in your code more easily. In this tutorial, you add an event to the Amazon EventBridge schema registry. You create an account-created event, which includes a user's name and email address. Navigate to the Amazon EventBridge console and choose Schemas from the left panel. There are 3 types of schemas represented in the tabs: AWS Event Schema Registry, Discovered Schema Registry, and Custom Schema Registry. When you choose AWS Event Schema Registry, you can search for any AWS service or event that's supported by EventBridge. There, you can view the schema for that event. To create a custom schema registry for your application, navigate to the Custom Schema Registry tab and choose Create Registry. Enter a name for the registry and then choose Create. There are currently no schemas in the registry, so to create one, choose Create Custom Schema. Choose your registry as the destination and call the schema User. You can choose to load the schema template using an Open API format from the Load Template option. You can then manually enter data for each of the fields. Alternatively, you can have the service discover the schema from JSON. Remember that events are written in JSON. Choose the Discover from JSON tab and enter the following code: ID 1, name Talia Nasi, email address talia@thisismyemail.com. Then choose Discover Schema. EventBridge extrapolates the schema from this information. The schema shows that the ID is a number, the name is a string, and the email address is also a string. Choose Create to create the schema. When you choose your schema from the schema registry, you can see the structure of the event that you just created. Once a schema is added to the registry, you can download a code binding, which allows you to represent the event as an object in your code. You can take advantage of IDE features such as validation and autocomplete. Code bindings are available for Java, Python, or TypeScript programming languages. You can download bindings from the Amazon EventBridge console or directly from your IDE with the AWS Toolkit plugin for IntelliJ and Visual Studio Code. From the EventBridge console, navigate to your schema and then choose Download Code Bindings. Choose the programming language you prefer, and then you'll be able to download it. This downloads the code binding to your local machine. You can also choose to download code bindings directly to your IDE with the AWS Toolkit. This tutorial uses VS Code, but again, you can also use IntelliJ. Ensure you have VS Code installed, and then navigate to the VS Code Marketplace and search for AWS and install the AWS Toolkit. You may have to restart VS Code. Choose a profile to connect to AWS and make sure you set the region to the same region that you created the schema in. You see this icon on the left panel, and when you access the AWS Explorer, choose Schemas from the left panel, then choose your schema, My Registry. Open User by right-clicking and choosing View Schema. You can now use this event object in your code. Let's talk about the benefits of event-driven architecture and why you could have challenges with request-response architecture. When starting to build a new application, many developers default to a request-response architecture. A request-response architecture tightly integrates components, and those components communicate via synchronous calls. While a request-response approach is easier to get started with, it can quickly become challenging as your application grows in complexity. In a typical e-commerce application that uses a synchronous API, the client makes a request to place an order, and the order service sends the request downstream to an invoice service. If successful, the order service responds with a success message, confirmation number, etc. In this initial stage, this is a straightforward connection between the two services. The challenge comes when you add more services that integrate with the order service. If you add a fulfillment service and a forecasting service, the order service has more responsibilities and more complexity. The order service must know how to call each service's API from the API call structure to the API's retry semantics. If there are any backwards incompatible changes to the APIs, the order service team must update them. The system forwards heavy traffic spikes to the order service's dependency, which may not have the same scaling capabilities. Also, dependent services transmit errors back up to the stack to the client. Now you add new downstream services for fulfillment and shipping orders to the e-commerce application. In the happy path, everything works as expected. The order service triggers invoicing, payment systems, and updates forecasting. Once payment clears, this triggers the fulfillment and packing of the order, and then you inform the shipping service to request tracking information. However, what happens if the fulfillment center cannot find the product because they are out of stock? Fulfillment might have to alert the invoice service, then reverse the payment or issue a refund. Would the system trigger shipping if fulfillment fails? Maybe not, since it's directly before shipping in the chain of events. Forecasting will also need to be updated to reflect the change. This remediation workflow is all just to fix one of the many potential unhappy paths that can occur in a synchronous API-driven e-commerce application. In a synchronously integrated application, teams need to coordinate any new services that are added to the application. This can slow down each development team's ability to release new features. Imagine your team works on the payment service, but you weren't told that another team added a service, a reward service. What now happens when the fulfillment service errors? Fulfillment maybe orchestrates all the other services. Your payments team gets a message and you undo the payment, but you don't know who handles retries and error logic. What happens if the reward service changes vendors or has a new API? How does that affect all of the other microservices? Ultimately, it's very hard to coordinate these orchestrations and workflows as systems become more complex and managements add more services. Event-driven architecture can help solve the problems of the close coordination of microservices, error handling and retries, and close coordination between development teams. In event-driven architecture, the publisher emits an event which is acknowledged by the event bus. The event bus routes events to subscribers, which processes events with self-contained business logic, and there is no direct communication between publishers and subscribers. The publisher and subscriber are decoupled. Coupling is a measure of how dependent each component of the application is on one another. Coupling can take various forms. For example, systems may be coupled by a shared data format dependency, binary, XML, JSON, or a temporal dependency, the order in which the components need to be called, a semantic dependency, or a technology dependency, Java, C++, Python. When the components of a complex application are tightly interdependent, it can be difficult and risky to make changes within one component, knowing that those changes will impact other components. This can slow down development processes and reduce feature velocity. Tightly coupled components can also impact the scalability and availability of the application. If two components are dependent on synchronous responses from one another, a failure in one component will bring down the other. These single points of failure reduce the resilience of the application. Reducing coupling between components means reducing the amount of knowledge that each component needs to have about the others. By using events to communicate between components, the components themselves only need to be aware of the format of the events or the event schema. They don't need to have knowledge of the component that sent the event or need to understand the behavior of downstream components like error handling or retry logic. Decoupled applications enable teams to act more independently, which increases their velocity. Another reason to migrate to event-driven architecture is to handle unpredictable traffic. E-commerce websites like Amazon.com have variable amounts of traffic depending on the day. Once you place an order, a bunch of things happen. First, Amazon checks your credit card to make sure you can pay. Then Amazon has to get the merchandise off the shelves and onto the trucks, and that all happens in an Amazon warehouse. There's no synchronous API call for the Amazon backends to package and ship products. After the system confirms your payment, the front end puts together some information describing the event and puts your account number, credit card info, and what you bought in a packaged event and puts it into the cloud and onto a queue. Later, another piece of software will pull it off and start the packing, shipping, etc. The key point about this process is that these processes can all run at different rates. Normally, the rate at which people click place order and the rate at which warehouses can get the boxes out of the doors are roughly equivalent. However, on days like Prime Day, Black Friday, etc., people hit that button immensely faster than the warehouses can operate, and that's okay because the backend will work itself through. E-commerce applications like Amazon.com need to be able to scale up to handle unpredictable traffic. When a customer places an order, an event router like Amazon EventBridge receives the event, and all of the downstream microservices are able to pick up the order event for processing. Because each of the microservices can fail independently, there are no single points of failure. Event-driven architectures promote development team independence due to loose coupling between publishers and subscribers. Applications are free to subscribe to events with routing requirements and business logic that are separate from the publisher and other subscribers. This allows publishers and subscribers to change independently of each other, providing more flexibility to the overall architecture. Decoupled applications also allow you to build new features faster. You may need to add a new event or just modify an existing event. Now let's look at some of the use cases for EDA. One of the most overlooked areas where developers and operators often start with EDA is around IT automation. AWS emits all sorts of events around areas such as start and stop of EC2 instances, logs being processed, security events, and many others. Oftentimes, it is as simple as subscribing to these events with Lambda functions as consumers of events to do things like validating configurations, reading specific tags in a log, or auditing user behavior. More sophisticated applications have risen from these use cases, sometimes referred to as AI ops, to use machine learning against your operations. Data processing is the next area we see as a huge benefit for EDA. As new sources of data emerge, you can subscribe to data pipelines to do machine learning, data transformations, data replication, or any other type of data processing. Event streaming refers to the constant stream of data into a stream, and EDA is often used here. Microservice-based applications often benefit from event-driven architecture by decoupling real-time processing and allowing systems to scale. In addition to synchronous APIs, microservices can use messaging or streams to communicate state changes or to send processing to happen at a later stage. Such decoupling will allow applications to evolve independently and allows individual components to scale. Event sourcing is often used in microservice applications to communicate state changes as they happen. This allows different applications to subscribe to state changes. To learn more about event-driven architecture and Amazon EventBridge, head to serverlesslands.com, where you'll find more content from me and my team. I'm Talia Nasi. Thanks for tuning in.